So this is in some ways a continuation of a video previously where we look at this integral from 0 to pi over 2 of natural log of cosine of x without the squared. So in this video we want to look at a similar integral with the squared, and I think what you'll see is that you have to go through a lot more work to calculate this integral, and you get to look at a lot of nice tools. And so some of those tools are as follows. So this series expansion of the natural log of u plus 1, so this is the sum n equals 0 to infinity of minus 1 to the n plus 1 u to the n over n. So we'll prove that. Another thing that we'll do is show that the natural log of cosine of x has the following expansion. So this is as a Fourier series. So we have the sum n equals 1 to infinity minus 1 to the n plus 1 cosine of 2nx over n minus the natural log of 2. And then also, if you take this integral from 0 to pi over 2 of cosine 2nx and cosine 2mx dx, you get pi over 4 if n and m are the same, and you get 0 if they're not. And we can put that all together into this Kronecker delta symbol, this delta mn. Okay, and then some things that we won't prove are this, which follows from Euler's formula for e to the I theta. So we have cosine of theta is e to the I theta plus e to the minus I theta all over 2. And then this thing, which we proved in a previous video, that the integral from 0 to pi over 2 of natural log of cosine of x is minus pi over 2 natural log of 2. Okay, great. So now let's get on with this first bullet point. So what we want to do here is take this natural log of u plus 1 and realize it as the integral of 1 over 1 plus u du. Now we can rewrite this very simply as 1 over 1 minus u du, so the antiderivative of that. But using geometric series where the common ratio is minus u, that is going to be the antiderivative of the sum n equals 0 to infinity of minus u to the n du. Okay, so now we're going to exchange the integral and the sum, and we're going to do that without really worrying about convergence, because in the region that we are dealing with, we have absolute convergence. So this is going to turn into the sum n equals 0 to infinity of the antiderivative of minus 1 to the n u to the n du. Okay, so we've got something like that. But now that's a really simple antiderivative, so that's going to give us the sum n equals 0 to infinity of minus 1 to the n u to the n plus 1 over n. N plus 1, I should say. And now we can make a very simple change of variables. So we'll replace n with n minus 1. And that's going to change this into the sum n equals 0 to infinity of minus 1 to the n minus 1. But notice n minus 1 and n plus 1 have the same parity, so I might as well put n plus 1 here. And now I have u to the n over n. And this sum should be from 1 to infinity. Okay, good. So that verifies this first bullet point. And now we're ready to move on to verify this second bullet point. So let's start with this left-hand side. So we have the natural log of cosine of x. And now I'm going to multiply this by 1, and I'll do that in the following way. I'll write this as 1/2 times 2 times the natural log of cosine of x. But now using power rules for logarithms, I'm going to bring this 2 inside the natural log, and that's going to give me 1/2 natural log of cosine squared x. And that's just by the power rule for natural logs. Okay, so now from here, I'm going to add 0, and I'm going to do that in the following way. So this is equal to 1/2 natural log of cosine squared x plus the natural log of 2 minus the natural log of 2. So obviously if we add and subtract the natural log of 2, that's okay. But now what I can do is put a parentheses around these if I multiply this by 2. Okay? So that's going to give me 1/2 natural log of cosine squared of x plus the natural log of 4 using the same rule. That'll be the natural log of 2 squared. And then I have minus natural log of 2. Okay, good. Now I can use the sum rule for logarithms to turn that into a product within the logarithm. So this is going to be 1/2 the natural log of 4 times cosine squared of x minus natural log of 2. So now from here, we want to use a trig identity. So it's going to be this power reducing formula. So we know that cosine squared of x will be 1/2 1 plus cosine 2x, but the 1/2 and the 4 will cancel in a certain way. And so we'll get 1/2 natural log of 2 plus 2 times cosine of 2x. Now we have minus natural log of 2 still hanging on. So the next thing that I want to do is I want to use this formula for cosine, but I'll have cosine of 2x instead of cosine of theta. So let's see what we get there. So this is going to be 1/2, and then we have the natural log of 2 plus, we'll have 2 times this 2 in the denominator. Those will cancel, and we'll have e to the 2ix plus e to the minus 2ix minus natural log of 2. So that's what we have. Okay, great. Now I'll bring this part up to the top and then we'll keep going. So on the last board we ended at this point. So we have natural log of cosine of x is 1/2 natural log of 2 plus e to the 2ix plus e to the minus 2ix. And then minus a natural log of 2. Now, the next thing that I want to do is do a fairly tricky factorization of the argument of that natural log. And the factorization will look like this. We'll have 1 plus e to the I 2x times 1 plus e to the minus I 2x. And then finally, minus natural log of 2 is still there. So now let's just check that that works. So notice we have 1 times 1 is 1, obviously. E to the I 2x times e to the minus I 2x, that's going to be e to the 0, which is 1. And so that added to the previous one will give us this 2. And then finally our cross terms are this e to the I 2x times 1 and this e to the minus I 2x times 1. And so that'll give us everything that's left. Okay, fantastic. Now what we can do is we can use a product of things inside a logarithm to turn that into a sum of logarithms. So we'll have 1/2, and now we have the natural log of 1 plus e to the I 2x plus the natural log of 1 plus e to the minus I 2x. And then we still have this minus natural log of 2, which is hanging on. Okay, great. Now we can use this first thing that we proved, which was that the natural log of u plus 1, in other words, 1 plus u, is this infinite sum. So let's do that. So that's going to be 1/2, and now we're going to have a sum of 2 infinite sums. So the sum n equals 1 to infinity of minus 1 to the n plus 1. And then here we're using this sum with u equals e to the I 2x. So that's going to look like e to the I 2x all to the nth power over n. So that's what we get for this first one. And then for the second one, we'll have something very similar, but just e to the minus I 2x. So this is going to give us the sum n equals 1 to infinity of minus 1 to the n plus 1, e to the minus I 2x, all to the nth power over n. And then we got to keep this minus natural log of 2 hanging on. Okay, now we can put these together. So I'm going to take this 2 and distribute it through, and then also add those sums together to see what we get. So notice that's going to give us the sum n equals 1 to infinity. We have minus 1 to the n plus 1 over n. Great, so I factored that n out of both. And then using exponent rules on these exponentials, we get e to the I times 2nx plus e to the I times 2nx, and that one is negative. And then this is going to be all over 2, and then we have minus natural log of 2. Okay, great. But now again, using this formula down here where theta is equal to 2nx, we see that we can turn everything in this sum right here is equal to cosine of 2nx. So making that substitution, we have that this is the sum n equals 1 to infinity of minus 1 to the n plus 1, and then cosine 2nx over n, and then finally minus natural log of 2. Okay, but that's exactly what we wanted to end up with. So we finished proving this bullet point. Okay, so now we're ready to move on to proving this third bullet point. So this says something about the orthogonality of these cosine functions. You can think about this integral from 0 to 2 pi as some sort of inner product, and these two functions are like the vectors, if you will. So I won't say anything more about that, but we will prove this identity. Okay, and we'll do that by using the following trigonometric fact, which says that cosine of alpha times cosine of beta is a half times the quantity cosine of alpha plus beta plus cosine of alpha minus beta. So let's see how we can use that. So the integral that we want to investigate is 1/2 cosine of 2mx times cosine of 2nx dx. But applying this identity, that's going to give us a half, the integral from 0 to pi over 2 of cosine of 2m plus n times x plus cosine of 2m minus n times x dx. Great. But now we have our hands on two functions that can be easily anti-differentiated. So let's go ahead and do that. So that's going to be equal to the following. And I'm going to spread this into cases. One case over here will be if m is not equal to n, and the other case will be if m is equal to n. So let's look at the case when m is not equal to n first. So that's going to give us a 1/2 out front. Now taking the antiderivative, we will have 1 over 2m plus n times sine of 2m plus n of x. And then plus 1 over 2m minus n times sine of 2m minus n times x. And then that whole thing needs to be evaluated from 0 to pi over 2. Okay. But we can do that very, very easily. Notice if we plug 0 into this, we get sine of 0, which is 0. If we plug pi over 2 into this, we get a multiple of pi inside of the sine function, and that's also 0. Now recall that m is not equal to n, so we know that we don't have a denominator of 0 there, so we're okay. So in both of these cases, you get 0. So we have 0 plus 0. Okay, great. Now if m equals n, we have the first term is essentially the same. So this is going to be 1 over 2m plus m. So that's going to be 4m. And then we have sine of 2m plus m. So in other words, 4mx. We're going to go ahead and evaluate that from 0 to pi over 2. Good. But now if m equals n, then here we have cosine of 0, which is 1. Now let's just put that here if m equals n. So if we take the antiderivative of 1, that obviously just gives us x. So this is plus x evaluated from 0 to pi over 2. So let's see what we have. If we plug in pi over 2 here, we get 0. Plug in 0 here, we get 0. So this whole thing zeroes out. I guess I should say what happens when m and n are both 0, but we're not actually going to deal with that case because notice it doesn't show up in this infinite sum that we're worried about. So maybe here at the top, say m and n not equal to 0, just to dot our I's on that. So let's see, we have 0 here, and then this 1/2 is multiplying everything. That obviously gives us pi over 2. So here we get pi over 2 times 1/2, which is pi over 4. So notice we get 0 when m is not in, and we get pi over 4 when m is in, but that's exactly what we wanted. We have pi over 4 times the Kronecker delta of m and n. So that finishes the proof of this bullet point. And now we're ready to tackle our main goal. So let's go ahead and open up a little spot for an equal sign here so we can work straight off of this. And so the first thing that we'll do is we will replace the natural log of cosine of x with this quantity right here. So let's see what we get when we do that. So we have the integral from 0 to pi over 2 of, so now we're going to have the sum n equals 1 to infinity, minus 1 to the n plus 1, cosine of 2nx over n, and then all of this minus the natural log of 2, then we're going to square all of that thing, and then obviously integrate with respect to x. Okay, so notice we have a binomial squared here. It's just our binomial is very, very complicated. This is one term from our binomial. That is another term from our binomial. So let's see what we get when we square that. So we're going to get the integral from 0 to pi over 2. Now I'm going to have the square of this series. So I'm going to have the sum n equals 1 to infinity of minus 1 to the n plus 1. Cosine 2nx over n, and then minus twice times the cross terms. Oh, and I should say this needs to be squared. And then minus twice the cross term, so that's going to be 2 natural log of 2. And then the sum n equals 1 to infinity of minus 1 to the n plus 1 times cosine of 2nx over n, and now plus natural log of 2 quantity squared dx. Okay, so that's what we've got going on here. So now I'm going to break this up into 3 integrals. The first integral will be what we get from squaring this infinite sum, and I'll let you guys look at the Cauchy product for infinite series in order to get a feel for what this is, but I'll just write it down and we'll talk through it a little bit. So this is going to be the integral from 0 to pi over 2, and now this series squared is going to give us a double sum, so I'll write it in the following way. So we have the sum m equals 0 to infinity, and then inside of that we have the sum n equals 0 to m. So we'll have minus 1 to the n plus 1, and then minus 1 to the m minus n plus 1, and then this is going to be over n over m minus n. Okay, good. And then next we're going to have cosine of 2nx times cosine of 2m minus n times x, and then dx. Okay, so what we have here, this is our first integral. And so how did we get that? Well, we're using this formula that says the sum n equals 1 to infinity, those should both start at 1, of a sub n quantity squared is going to be this double sum, m equals 1 to infinity, and then the sum n equals 1 to m of a m minus n. So that's a special case for squaring a series of the Cauchy product of two series. Okay, I'll clean up this little bit and then we'll see what we get out of this. Okay, so now we're going to move this integral inside of the sum and do some simplification. So notice this is going to give us the sum m equals 1 to infinity, the sum n equals 1 to infinity, and now we're going to have minus 1. Now we can take the product of these, so that's going to be m plus 2, but m plus 2 and m have the same parity, so that's just minus 1 to the m, and then this is going to be over n times m minus n. Okay, now we can bring that integral inside. So this is going to be the integral from 0 to pi over 2 of cosine 2nx cosine 2 times m minus nx dx. Okay, good. So now, the next thing that we can notice is this entire integral is equal to pi over 4 delta n m minus n. And so that's from this third bullet point right here. So what I'll do is I'll just erase this integral. I'll replace it with pi over 4 delta n m minus n, and then we'll move from there. Okay, so I've cleaned up what we had on the last board into the following. So I have delta n m minus n. So now notice this symbol is 0 most of the time. The only time it's not 0 is if n equals m minus n. In other words, if m equals 2n. So what that allows us to do is to collapse this sum to the cases only when m equals 2n, and that's going to give us the following. So this double sum will collapse to a single sum, and the single sum will look like this, pi over 4, and then the sum n equals 1 to infinity of minus 1 to the 2n, because notice m is equal to 2n here, and then n, and then notice m minus n is also going to be n, and then m minus n is also n, so that's going to give us n squared in the denominator. Okay, so this double sum collapses to this nice single sum. But notice that minus 1 to the 2n, well, that's always going to be positive because that's minus 1 to an even power. So I can erase that, replace it with just 1 over n squared. But we know exactly what 1 over n squared is. That sum, it's Euler's famous sum, which is pi squared over 6 multiplied by pi over 4 gives us pi cubed over 24. Okay, so that's only this first integral. So what I'll do is I'll erase the board and I'll replace this first integral with pi cubed over 24, and then we'll move on. Okay, so now on the last board we argued that this first part of the integral becomes pi cubed over 24. Now we want to worry about all the rest of the parts of the integral. So, and I'm going to do those one at a time. So notice here we get minus 2 natural log of 2, and then we're going to have the integral from 0 to pi over 2 of this thing right here. So this is the one that we're focused on now. But notice that this term, which I've overlined in red, is a portion of this guy over here. In fact, if I add natural log of 2 to both sides, I'll have exactly natural log of cosine of x plus natural log of 2 is equal to this guy right here. So in other words, I can replace this with natural log of cosine of x plus natural log of 2, and that's exactly what I'll do. So here I'm going to have natural log of cosine of x plus natural log of 2 dx. Okay, so there we've got it. And then finally, I have plus the integral from 0 to pi over 2 of natural log of 2 squared dx. Okay, and now we're ready to keep going. So this is going to give us pi cubed over 24 minus 2 natural log of 2. And now notice that the integral from 0 to pi over 2 of natural log of cosine of x, we did that in a previous video, and that's going to be minus pi over 2 natural log of 2. Good. And then the integral from 0 to pi over 2 of natural log of 2 is going to be plus pi over 2 times natural log of 2. So those guys are going to cancel out. And then finally, this integral over here of a constant, which is natural log of 2 squared from 0 to pi over 2, is going to give us pi over 2 times natural log of 2 squared. Okay, so now we're ready to just write the answer down. So we get, this is pi cubed over 24 plus pi over 2 natural log of 2 quantity squared. And so that is the value of our goal integral. So that finishes this video.